Hello everyone, my name is Omi, and today we're going to be going over the ladder problem. At first, or personally, I struggled with this, but once you learn the method and how to go about it, it becomes fairly easy to do. So let's just get started with the question. A 24.4 kilogram person climbs up a uniform 141 Newton ladder. The upper and lower ends of the ladder rest on frictionless surfaces. The bottom of the ladder is fastened to the wall by a horizontal rope, and the angle between the horizontal and the ladder is 56 degrees. Find the tension in the rope when the person is 1/3 of the way up the ladder. So the first thing you want to do for a ladder problem, and honestly most physics problems, is you want to make a free body diagram. So let's just get started with that. We can do the ground here, we can do the wall right here. We can make this the ladder. Okay. So now, as per how to do free body diagram, we're just gonna note down all the forces. So in the question, it says that the upper and lower ends of the ladder are frictional surfaces, so there's no friction. However, we do know that the wall is going to exert a normal force on the ladder, call that Fw, and we know that the ground is also going to exert a normal force. We can call that Fn. We know that there's the tension of the rope, call that T. We know that there's the weight of the ladder, call that Fg. And then there's the weight of the person. We'll call that FP. So the best way to go about solving pretty much any physics problem is you want to solve it in terms of like symbols and variables first without plugging the values, and once you have like a equation full of variables, you can just plug in the values later. So to begin, you want to break down the question into three parts. You want to break it down into the horizontal forces, the vertical forces, and the torques, because breaking it down into these three parts will allow you to identify the unknown variable, which is the tension, much better. So firstly, we know the ladder is at rest. Therefore, the sum of the horizontal forces is going to be equal to 0. Also, the sum of the vertical forces will also be equal to 0. Finally, also the sum of the torques will also be 0. So torques is where it gets a little bit complex, but let's just go with the horizontal and vertical forces for now. So let me just do this real quick. So for the horizontal forces, we know that there's only two. There's just the normal force of the wall and the ladder, and the tension force. So now we'll take right as positive and left as negative. Because the tension force is acting to the right, we can set the equation up like this. The tension force, sorry about that. The tension force minus the force of the wall, or the normal force of the wall, is equal to 0. You can just change that to the tension force is equal to Fw. Now this is important because we know that what we're solving for T, or the tension. So if we figure out this Fw, we'll be able to pinpoint what T is. So next, there's the vertical forces, Fy. So we know there's only three vertical forces. There's Fn, which is the normal force. We know there's the weight of the person and the weight of the ladder. We'll just take up as positive, down as negative. So we can say that the normal force minus the weight of the person minus the weight of the ladder is equal to 0. Just redo that, make it Fn is equal to force of the person plus the force of gravity. Okay, so now with the torques, this is when things get a little bit more complicated. So firstly, I just want to go over the torque equation, right? So the torque equation is torque is equal to the perpendicular force times distance. So now that we know firstly, let's just identify what forces are producing torque. We know that Fn and tension force are not producing any torque because they're acting about the pivot point. And that's another thing. You want to identify a pivot point first to determine which forces actually produce torque. So we know only the weight of the person, the weight of the ladder, and the normal force put from the wall onto the ladder are the only things that are going to produce torque. But if we look at the torque equation, we know that we're going to have to break the forces down to find the perpendicular component, because the equation is perpendicular force times distance. So what we can do here, start off with Fw, because it's the easier one. We can break it down into components, and we want the vertical component, and we're looking for this right here. This is perpendicular component. We know that angle theta here is going to be the same as the angle theta over here, because interior angles are equivalent. So we know that the perpendicular force, or the perpendicular component of Fw. By the way, this symbol just means perpendicular, is going to be Fw sine theta. And the reason we chose sine is because it is on the opposite. It is the opposite on the opposite of the angle. Next, we're going to want to go over the. Next, we want to find the perpendicular part of the Fg and Fp. So we're gonna break it down like that, like that. So we're looking for this component, and that means we're gonna need to find this angle. And luckily enough, we actually already know this angle because it is equivalent to this angle. And if you already know why, you can skip ahead a few seconds, but I just want to explain why really quick using this. So just to get started, this is going to be, we can call this one Fg, right? This will be the Fg, or the weight of the ladder going down. This is the vector. And here we're breaking it down into components. So we know that angle theta is here. We can just make an arbitrary variable for the complement, call this alpha. And because alpha is up here, that means it's going to be equivalent down here, as like previously said, interior angles are equivalent. So because these two are the same and there's two right angles over here because they're both right triangles, we know that theta is going to be the same up here where the components are going to be. And we're looking for this component in this situation because this is going to be the perpendicular, so we're going to use cosine theta. So let me go back over here. So again, we're going to be using cosine theta here because it's on the adjacent side, and we use sine here because it's on the opposite side. So we know that the perpendicular, the perpendicular of Fg and the perpendicular of Fp, or the weight of the person, is going to be Fg cosine theta, and again Fg or Fp cosine theta. Now that we have that out the way, we can finally start doing our torque equation. So for our torque equation, let's say start over here. So we know let me just say this as well. The positive direction for torque is considered clockwise, and the negative direction is considered counterclockwise. So we know that Fw is going to be acting counterclockwise, and Fp and Fg are going to be acting clockwise. So let's do that really quick. So we know that because the torque, the sum of the torques equals 0, we can say that the torque of the person plus the torque of the ladder minus the torque of the normal force of the wall equals 0. And the reason these two are positive because they're both clockwise, and this one is counterclockwise. So again, we can just restructure that and make it T, or a torque of W, equals the torque of the person plus the torque of the ladder. So now we can break this equation down a little bit further. So if we go back up here, we can see that the equation for torque is equal to the perpendicular force times R. So now luckily we just broke the perpendicular forces down here. So now let's finally start breaking it down. So you may be compelled to first put, okay, we can just do Fw sine theta times Rw, which is just the distance of one whole ladder length. But remember up here, we said that T is equal to Fw. So we can just, instead of saying Fw, we can say T, so we can actually find the equation. So we can put it here. So T sine theta times the Rw equals the weight of the person, which is Fp. You can say Fp cosine theta times Rp, which is just how far up, the distance of how far up the person is, plus Fg cosine theta times Rg. So one way you can make this equation way easier is just by putting all of the other distances of the torques into like the same, like making it the same variable as Rw. Because if we look back up at the problem, we know that Rw is just one whole ladder length because it's up here, and because the ladder is uniform, that means the center of gravity is going to be halfway. So the force of Fg is just going to be halfway up the ladder, and it says that the person is 1/3 up the way of the ladder. So instead of saying Rp, which is how far up the person was, we can just say 1/3 Rw because they're 1/3 of the way up. And for Rg, which is how far up the force of the ladder was, we can just make it as 1/2 Rw because the force is like acting right in the middle of the ladder. So now that we finally have that, we can kind of combine. We can just write out the equation now. So T sine theta times Rw equals the force of the person times cosine theta times 1/3 RW plus the force of the ladder times cosine theta times 1/2 RW. And you may have noticed now we can cancel out all the RWs because it's in every part of the equation. Cancel out RWs. We can also just, in this case, we can just now also at the same time divide by sine theta to get t by itself. So finally we have t is equal to the force of the person. Now instead of writing the force of the person, if we go up here, the only thing we know about the person is their mass, and we're going to have to change that into newtons. So we can just, instead of saying the force of the person, we know that obviously force equals mass times acceleration, right? F equals ma. So we have the mass of the person, and we can just use the acceleration due to gravity, call that g. So we just say mass of the person times g. Go down and put that in. So we can say, it's right here, the mass of the person times g times cosine theta times 1/3, because we got rid of r, plus, and the ladder is already given to us. We already have the force of the ladder. It's just 141 newtons, so no need to change that. We can still call that Fg. So we have Fg cosine theta times 1/2. Then finally divide all of that by sine theta. So now we can just plug in all of these values up there. So we know that the mass of the person, or the tension, is equal to the mass of the person, which is 24.4 kilograms, times the acceleration due to gravity, which is 9.8 meters per second squared. We'll just use 9.8 in this instance. And then times cosine of theta, and theta is just 56. Oh, sorry. 56. And we can just multiply by the 1/3. We'll just do the 1/3 over here. That will be easier. Plus 1/2 Fg is 141 newtons, the weight of the ladder, times cosine of 56. We already have the 1/2 here. Divided all of that by sine of 56. Sorry, 56. That should, and once you put all of that into the calculator, if you put it correctly, your final answer should be 101.3 newtons. Thank you guys so much for watching. Basically, just to make a long story short, this was a really long problem. The main things you should do is just break the equation down into the horizontal forces, the vertical forces, and the torques, and just solve from there. If you guys have any other math or physics problems you'd like me to go over, please let me know in the comments below. Thank you so much for watching, and have a great day.